So hello everyone. Today we're going to do February's USACO Gold Contest. And we'll kind of discuss how I would approach some of the problems and what it would look like to actually participate in the contest. So we'll get started. We can. All right, so we'll get started. All right, so we have 3 problems. So open all of them. Okay, so we have redistributing gifts. So in this case, n is really small. It's like this. We have n cows, and we have a list of preferences. And then we're given these queries. Okay, so we want to see if we can wait to like permute the gifts that are currently assigned in order to still be consistent with like the preferences. But we also have some restrictions in which reassignments we can make. So I'm not entirely sure how to solve that. It's a little bit similar to one of the silver problems. So I have a couple ideas, but we'll come back to that. Okay, so in this case, we're given a problem. Bessie submits this code, which has a half probability of getting 1 test case, has a quarter probability of getting 2, has an 1/8 probability of getting 3, and so on, up until there's no more test cases. And we want to know what is like the expected score she can get if she makes an optimal strategy. This sounds like it's probably like some sort of classic problem, and actually sounds as a very simple problem statement. This one might be worth thinking about it. You can come back to that. And we have this one. So we're going to n 10 to the 5 cows. I would like to connect them in a network. I guess the edges are weighted like that. This sounds like it's just minimum spanning tree, but I guess the issue is the number of edges is very dense, so you have to be careful. This might be quite simple to do. Okay, so those are the 3 problems. Number 1, it's not obvious to me how to solve. Number 2, I guess, what's the constraint here that makes this would be minimum spanning tree? Okay, I think I'm going to think about the 3rd one first. So that's what is the name of this problem? Moo Network. So in this case, Moo Network. This looks like MST, but we use Euclidean distance squared as edges. So I don't know if there's any techniques that like allow, because for example, for Manhattan distance, there's actually a standard technique for doing MSTs on Manhattan distance, but I don't think, I mean, that obviously won't work for this, but I don't know if there's any specific techniques here. The other thing that I noticed is yi is less than or equal to 10 is less than or equal to 0. And so, our naive algorithm naively, we would have O of n squared edges, which would be too slow, right? If we can eliminate some of the edges, I think we can have a solution here. And I guess if we're looking at some point like x comma y, we only would want to connect to the first one in each column. So because there's, and so on. So if there's a cow here, cow here, cow here, cow here, cow here. Because you never want, if there's like 2 cows in the same columns, but on the same y coordinate, you wouldn't want to, if you took this edge, you could exchange it for this edge in MST. So each only needs 11 edges coming out. But I guess you also need the ones that go on the same level. You probably want those. But approximately 11 edges. And this would give us like an O of n plus like 11 times n or something. Because there's a few ways to compute MSTs, which since it's a gold contest, most of you guys are probably aware. We can do something like prims or Kruskal's, but yeah, I guess in this case, we'd actually end up with O of like n log n if we use Kruskal's. And so these are standard algorithms for computing MST. So as long as we can reduce the number of edges, if we reduce total edges, we can just, okay. So all I have to do is reduce the total number of edges. And I think we can do that just because they made yi is very small. So I think this one will be pretty simple. This one we definitely do the math for and try out some cases. And then this one, yeah, we're gonna have to spend some time about that. So let's get this one out of the way because I think we know how to do it. Start by putting a template. So we need to take on the cows, and we can sort the cows. So we'll do here, make an array for all the cows. But create graph and then run. We'll go with prims just because prims is pretty simple. We don't need to like Kruskal's is usually a little more code, in my opinion at least. Okay, so we'll start with an input. And to get the graph. Construct the graph. We need to make sure we make sure we use long. X is up to 10 to the 6, so it could be 10 to the 6 squared. So here, we'll store the last one seen for each y coordinate. Now we'll move over the cows. One thing we want to do is we want to connect adjacent cows level and connect to all the cows. So we want to connect to this cows on the same level. Make a little function to add an edge. So here, I guess we can compute the cost here. Use the function they gave us. First. We'll add the edge. So now we just need to loop over all the y's. Y not equal to negative. Last I equal to -1, we'll add the edge from I to last of y. And then here we can run rims. Rims is a pretty standard algorithm. It looks a lot like Dijkstra's. So if you've seen Dijkstra's, the code is almost identical except for one minor change. So we're going to store where we are. So the int will be our location and LL will be our current cost. We need to make sure it's a min heap. So this is the way you can make it a min heap. You also need to keep track of which ones are visited. So we can do start at any one, we'll start at 0. Wow. That's empty. You got the top element. If visit t that second, so we already visited it, we can just continue. Otherwise, we mark it visited. Answer. This is the first one, and now we just over and push in the new. Okay, so here it will be p dot second. P dot make sure the files, and we can. $663. Close, but not it. Also weird that's like off by 1. Wouldn't be what I expected. Prints, at least see what edges are being added to the graph. I don't know if this is a little hard to see, so I'm going to make this bigger in general. Well, that's easier for you just to see. You can ignore the warnings. Those are not because of the code. I wonder if that's actually the correct answer for the sample. Maybe we're doing something silly and maybe it's actually. Why would it be? Add some more debugging prints and see what we can see. Okay, so we end up adding the node 0 with cost 0, 1 with cost 162. 2 with cost 205. Seems like some of the edges aren't being added. Oh, that makes sense. Okay, so I think I know what the bug is. Edges. Last of cow divided by second equals I. So when we see a cow that we previously processed, we'll update last. Small bug, not too hard to fix once we've noticed it. You know what, that does seem correct on the sample. Maybe we should just try submitting it. Of course, with USACO, there's no penalty for using the judge to help you submit. So we'll just see what the judge says. Okay, so we will submit it real quick. I think we're good. Let's see. This seems like a really simple problem, especially for gold, because like if the trick is just realizing why I's are bounded, like that seems like this is meant to be a pretty easy problem. The other thing I thought when I saw like yi less than equal to 10 is maybe like you do some sort of like bitmass DP, like down the grid, but with how, I mean, once you realize MST just works, I guess, because it seems to fast everything, then that's it. So, you know, they also doubled the time limit. I don't know if that was necessary because it seems that we were well within the 2 seconds. So, yeah, that was a really quick problem. Of course, it's a smart move to do the one that you know how to do first, and so we can ignore this problem now. Okay, so let's think about cow camp. I think this one, yeah, I think the solution to this is probably pretty quick, but okay, there's 10 to the 3 test cases, but 10 to the 9 is huge. So even if you could compute this in a tabular way, like sort of doing dp over k, you know, we have to get around k being that large. So either we end up with like a concise formula in terms of k, or maybe there's only so many unique values for t. Maybe we have to take advantage of that. But let's think about this. Okay, so we have cow camp. So what is the expected value in one run? Let's just call that E sub t. It'd be like 1/2 times 1. I think is the sample included? Yes, I think you get the sample case for free. So you can't get 0 test cases. And then you get, you know, if t equals 2, then E of t equals 1/2 times 1 plus 1/2 times 2. Otherwise, this is like 1/4 times 2 plus 1/8 times 3 plus. And so on, 1/2 to the t times t plus 1/2 to the, however you want to, I guess we'll end up like t minus 1, t minus 1, t minus 1, t. So we can compute it for the single case. So k equals 1. I guess what's the strategy here? So if we have 2 flips and we get a score, let's say our score is like x. Of course, there'll be some, you know, strategy will check if x grand equals some cutoff, say, I don't know, y, then don't not roll again. Well, don't submit again. If x less than y, then submit again. I guess I don't really know if the equality matters. I don't think it does. So I guess only resubmit. If current value less than future expected value. So I guess if we're on two moves, we want to check if x is greater than or equal to ET, don't or submit. If x is less than ET, resubmit. So this means that the expected value for, I don't know, let E sub E of K be expected value for K submissions. T test cases. Okay, so I guess if we're going to look at E sub T of 2, this equals the probability x is greater than or equal to E sub T of 1 times the expected value of x given that x is greater than or equal to ET of 1. So in the case we get something greater, we want to know what is expected value of something greater times the probability we actually get something greater. Plus 1 minus P of x greater than or equal to ET of 1 times just the remaining probability, so ET of 1. So I guess we can try this out in the sample. The probability distribution on x is like x has a 1/2 chance of being 1 and a 1/2 chance of being 2. So in this case, E of T of 2 is equal to, I guess the expected value to begin with is 1.5, right? So E of T of 1 equals 1.5. E of T of 2 equals the probability you get something greater than 1.5, which is 0.5 times the expected value if you were greater than 0.5, which is 2, right? Plus 0.5, again, 1 minus the 0.5 is 0.5 times the overall expected value, so 1.5. And this gives us 1.75. I guess on the problem we're looking at K being 3, we should get 1.875. We can confirm that, hopefully. Again, 2 is still the only one greater. And I guess that does work out to be 1.875. So it seems we keep applying this K times till we get the answer. So some things you notice is we can pre-compute probabilities for x greater than or equal to like some value v, and the expected value of x given x is greater than value v. I guess another way you can write this, if we look here, we can also write this part as just the sum of x times p of x equals x for x, right? v greater than or equal to e t of 1. So you can write it in that form too. So we can pre-compute this. We can answer these in O of 1. The issue is this would give us an O of K algorithm, or O of K plus T, because you have to do the pre-computation, but T is much smaller. This is too slow. it's k. Otherwise, we're going to 10 to 9. So we're going to try something else. I guess we could also check that this works in the other test case. I think I feel about the formula though. You know, there's like a common technique where like we want to apply something like a formula some number of times. We don't like at some point it kind of changes, right? Because if you look here, these terms, like these remain the same until your expected value crosses an integer. So if there's a way for us to compute where it's going to cross an integer and then skip over that. So if we can find a way to apply this like k times quickly, and then when we get to an integer, just stop and then reapply it. So we can apply it in like the number of times we get a distinct value that integers, but there's only O of t, or I mean, only t, not even O of t, possible integer values, because that's the only, you only get a score between 1 and t test cases, right? So we can only have somewhere between 1 and t test cases that we get correct. And so our expected value will only change when we cross over one of the integers. So in this case, okay, let's see, is there a way for us to apply this? Let's look at this formula abstractly. We get f of some value x equals, you know, we have, this will be the summation of like x times p of x equals v for v greater than or equal to value t plus 1 minus some probability times like the previous values. So like e of t of k minus 1. Whatever, that's not too formal. But the idea is we're just going to look at this in an abstract manner. So let's just consider you have some function f of x that takes, you know, if we look here, this is constant until you pass an integer, right? So let's just call that a constant a plus b being 1 minus p times x. So x to f of x applies the strategy 1 summation. So it's like we're building a table and you could just keep applying this for different values, a and b, whatever. But let's say we want to apply f k of x equals a plus b times a plus b times a plus b. And there's somewhere an x in there. So I think the thing to notice, we're going to end up with a plus ab plus ab squared plus so on. Plus all the way up to b to the k times x. I think we get a to the b k minus 1. So we can actually compute this because this is a geometric series. So in this case, if we want a geometric series, an infinite geometric series, you may remember, if we look at like an infinite geometric series, a plus ar squared, and so on, this equals a over 1 minus r, as long as r is as opposite value less than or equal to 1, or less than 1, I guess, right? So in this case, we can use this formula to get, we get a times a over 1 minus b plus, it's not an infinite geometric series. We stop at the a times the b to the k plus 1. So this equals a plus AB plus dot 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 plus AB to the k minus 1 plus AK b to the k dot 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 minus AB to the k dot dot dot. This is an even infinite geometric series. So we can subtract it off. So what we can do is we can subtract off A times B to the k over 1 minus B. And we just need to add on the last term plus B to the k times X. This is equal to f of X given the parameters A and B already being fixed. And so that's just A times 1 minus B to the k over 1 minus B plus B to the k times X. This is equal to f of X. And so if A and B are fixed and don't change, then we can apply it k times really easily. We just need to figure out how many times to apply it. So if you have a current value of X, you want to know when you're going to cross an integer. You can maybe try to solve for what value of k makes this greater, but k is in the exponent. I don't know if that's going to be trivial. The other idea is just we can binary search on how many times to apply f of X. So yeah. And I guess we're only going to skip t times, so we only have to binary search. Binary search O of t times. So this should be like something like O of t log k, which is much better than O of t plus k, which did not work, right? We know that we cannot do that. But this seems like it'll work. I don't know if there's just anything too tricky here. Maybe this is what I'm doing. This seems like a pretty simple problem. I guess you just have to realize the game theoretic property of like when is it optimal to switch? Well, of course, if your score is better than what you're expected to get, you should keep it, right? That's a reasonable intuition. You're just going to build back the table. And so, like, you could do dynamic programming and just build up this table. It's just tricky, but since the function is the same, we can kind of just combine the applications. And so I've seen problems where like, the technique is to skip past like huge chunks because nothing changes for I mean, that's a vague statement of that like quote unquote technique, but I mean, that's basically what we're doing here. So in this case, we'll just try implementing this. Template. In this case, we need to take the inputs and t. Use longs just in case we're afraid of overflow, because we're going to be like binary searching on them and maybe it would overflow. In this case, we have an input. Pre-compute tables plus probabilities. Also use long doubles just in case precision issues hurt us. I mean, like long doubles in C++ are 128 bits. A little bit better for precision, a little bit slower overall, but I don't think we're worried about speed here. So we need to compute, the probability for value of 10 to the 3 that we got. Yeah, t is not very large. You could definitely imagine t being larger, I think. Maybe there's another solution, but it's not bad. Let's compute distribution. I guess the probability of 1 is just 0.5. Always. Now we need to loop from t equals 2, t less than t equals plus. If t equals t, probability of t equals the same as the previous one, else probability t equals 0.5 times probability t less 1. You have to get one more correct to get the next score. So it just multiplies by 0.5 each time. Yeah. And now we can pre-compute prefix probability. And then the expected value. So T times probability. I'll write it down. T minus 1, T greater than equal to 1, T minus prefix probability of T equals prefix probability of T. And then prefix expected value, T equals prefix expected value T plus 1 plus T. We should be in these two like prefix sums, except they're, we're going down, but they're just prefix sums. Okay, so we have that. I want to repeatedly binary search. Let's start with K and then LD current. Current value will just be start with UT1. Just well, K is less than K. I'll just keep binary searching. So in this case, we're going to need a binary search. So we're going to need use longs again, just to so here we don't really know what the upper bound is. Of course, you could pick something like 10 to the 9 or something, because you're never going to skip more than that. Because I don't know the upper bound, I'm going to instead try. Okay, I think we need to. Here we just want to apply this function that we wrote, the one with return a times 1 minus power. Need that function. Or we could be on paper. I want to figure out what is the next integer we'll cross. So, okay, I guess we need to be what A. A in this case was just the prefix expected value. So that's just like the ones all greater than the expected value of it. And B is 1 minus prefix probability. So probably you're not greater than A comma B comma high is less than extent, then high times equal to 2. I guess the other thing we can check is that K plus high less than K. Of course, we don't want to let high just keep looping forever. I don't know if it would. Probably would find another crossing. Oh, but no, it would. You could end up having never reaching the next crossing point. So we don't want this to loop infinitely. Well, low is high. L times equals. How many times should we skip? Search. Mid less than extent, low equals minus 1. Else times equals high. Certain time. We should have found one that actually works. We didn't, then this binary search. Okay. Times plus K is greater than K times K minus K. not a lot of code. Uh, That's not good. So let's look at this. Yeah. I search somehow didn't find these solutions, which is not good. Did they even run? I guess it's possible there's never a crossing point in that case. Times start out at 5, I guess. Okay, what's going on? How is that infinite looping? That should not be possible because we'll eventually terminate. That's not, I guess, k plus equals. That seems to work. Test another sample. 2.315, is that correct? Let's see what our initial value is. .875. I don't think we computed the probabilities correctly because you don't terminate when you get the first test case wrong. Which for some reason I was assuming we did. So I think here this is incorrect. This should be pow 0.5 1. And here, this me like the choose function. But we can compute the choose function, choose of 1 equals n plus 1 over, or let's say just choose of r plus 1 equals n minus 1 divided by r plus 1 times. So you can multiply by t minus 1 minus t wait. So we're adding 1 to t. So t in this case is now 1. Something like that. Is it? Oh, because t minus 1 is our current r. Of course, we can work it on paper, but also can just double check 0.25. Big. Oh, there we go. That is. That's. Yeah, we just output our answer and it's done. We'll try setting this. See if we get it. No, something's wrong on that test. Oh, we're getting some of them. It's weird. I guess we should. K should equal K, right? We should never passed it. I wonder if add a small large. I don't know. I think we're probably the right solution. I feel like there's just issues with precision here because let's try it. If you're exactly at an integer, I feel like you're gonna make the wrong decision for like if you're technically before the integer versus after the integer. Is that less or more than before? That looks subtract. Let's see. What about these test cases? Five. I mean, the thing is, it's hard to know what's wrong when only 3 test cases fail. Yeah, like that assert and see. Oh yeah, we shouldn't even get that in the sample, to be honest. That's a little odd. Like, if we don't find anything, maybe then we'll do that case. I'm not really sure what I'm changing. Again, I don't know if this is a bug, but like with USACO, you really can just send as much as you want. So we're just gonna submit. I don't really know what. I would, like, is it because of precision anywhere? Is it because of, and maybe I can just like change the precision and see if we fail different ones. Maybe that would be a sign that like they still find the same 5 for some reason. It's odd. But maybe if it's precision, we'll get lucky. But like change the epsilon didn't change anything. That's weird. I don't know. They must have some bug somewhere. What about those 5 test cases? I guess we can go up to next in, but like they're floating points. Does it really matter? It doesn't matter. We can go up to next in. I'm guessing there's some sort of precision issues, but we're always getting the same result, so it's kind of hard to say it's precision issues, but the result doesn't seem to change. Yeah. Add another assert, see what that tells us. There. Still find the same ones. Okay, so if I don't get this, I might also move on to the first one and just come back to this because I think we have the right idea here. Like it seems weird for us to fail at just 5. And besides, that's a pretty good score. You would get promoted with that if you can get the other, so I don't know. I do want to think about this though. Like the only thing that occurs to me is like precision issues, but it's clear that's probably not any. Um, the chance that we passed these and had like the formula, the math wrong, it seems pretty low. So I'm not like not really worried about this part. 10 to 3 is I didn't make my raise large enough. I don't know. Oh shoot! Wait. I'm not so used to having a template, and sometimes I forget that. Like I never actually write that. But with USACO rules, I forgot to add the precision to the output. So it's possible we're failing those just because of precision. With the output, which explains why we weren't failing when we changed things. Like it was yeah, okay. That was kind of silly. And most of those submissions were kind of dumb, but there's no harm in trying. Okay, so we got this problem. So we're 2 down, 1 to go. Okay. So one thing we can do here for redistributing is gifts is think of it as a graph So we have some directed graph, and I think for the sample, 1 cannot be replaced with itself, 4 can have everything else, 2 and 3, so 4 points here, 4 points here, 4 points here. These point to each other, they both point to 1. So in this case, we want to know the number of ways you can decompose this into like cycles. So obviously 2 and 3 can switch, and the other ones there's no cycles that include 1 or 4, so it's not possible. There was a problem in silver, and I solved it with like strongly connected components. So I'm thinking, you could break it up into strong components, and that helps you get information about whether they appear in a cycle, or at least whether like each edge appears in a cycle. But here we need to answer queries. So instead, we're splitting up the graph into two chunks, and we're saying you can't exchange between. So you want to take a subset of vertices and compute the number of ways to decompose the graph into cycles, I think. Because like every permutation is decomposable into cycles. And of course, the cycles, if it's a valid assignment, must be cycles in the graph. But of course, you're allowed to point 1 to itself. So that doesn't count. Another thing to think about is like, I don't know, there's a concept of matchings on a graph. So maybe we want to like, if we think of it as like a bipartite graph, like which one do they receive the gift from and which one do they give the gift to? In this case, everything points to 1, because all of them give the gift to 1. But 2 and 3 can give it to each other. And 4 can give it to everyone. So here, like want to know the number of perfect matchings, because each one has to be paired with another one, and it doesn't matter, you could follow them to actually construct the cycles, but it doesn't even matter if you do that. So another way you can think about it, instead of like a graph like cycles, we can think about a bipartite graph, and this like number of perfect matchings in this bipartite graph. Or matching is, you pick 1 to assign 1 to, 1 to assign 2 to, 1 to assign 3 to, and 1 to assign 4 to without picking the same matchings. So like a valid matching could be this, 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 this. Or you can switch these and so on. It turns out you can't put 4 towards here, because then 2 or 3, depending on which one you get blocked. That's why 4 has to be matched to itself, because 4, it's the only incoming edge to 4. So I don't think number matchings is efficient, but n is less than 18, so maybe O of 2 to the n or O of n times 2 to the n. That is particularly small. And the 2 to the n probably come from like doing bit masks. So maybe we can, then your queries are just asking for the number of reassignments on a bit mask. So I could do like dp of a given bit mask. Pick a pair to assign and, recurse. So I think we could do some sort of DBs. You're gonna assign like the first non-assigned one and then pick the remaining one. And then you're just multiplying the product of like two bitmask lookups. And this would probably give you something like n times 2 to the n. So actually, the queries would be really easy to answer, and we just pre-compute this all. That might work. I don't think that SCC stuff works either, because like if you think of strongly connected components, you can't just permute them arbitrarily within a strongly connected component. You can any two that are in the same strongly component that preference actually exists, then yes, you can exchange them. But that doesn't hold in general. Like it doesn't help you assign the whole assignments. So I think we can think about coding this. See what we can. Okay, this is our last problem. So we have plenty of time. You know, there's no, in general, you shouldn't rush and USACO unless you, yeah. The third one is unexpectedly easy. Number two, it's a nice problem. Simple math. It's just this one. I don't want to rush to coding too quickly though. I think this should work though. And the bounds, of course, give us huge hints because ending at teen, like 2 to the n would work for about 20-ish, n times 2 would work for about 18-ish. So it's completely plausible that could be a reason it's n being 18, because yeah. Right. I don't think we really need to know. We can just construct the graph. Let's store them. Take it, and construct the graph. Here I'll make it 0 index, just make sure we don't run into any indexing issues. So this is the same preference. So that constructs our graph. We can compute longs. This is what's 18 factorial, 10 to 15. Okay, so it does need to be longs. Memo. That. Yeah, there's no ways to assign. One way to assign. Sorry. Yeah, there's one way to assign. You have 0. You just don't exchange anything. So we'll initialize the memo. Okay. I think we can do int. I think that gives you the least significant bit, and so we can. Okay, so that's 0. I guess that even tells the index. At least. Okay. Yeah. Okay. One. We're gonna pair off this one with something else, but it can be K itself. I guess the other thing to do is make sure they're allowed to connect themselves to do. Okay, so in this case, if adjacency K of B it should have been. Okay. Equals dp bm minus 1 with a K minus 1 with a B. I guess that B and this equals dp of B. Okay. Do a case work there. Okay. I don't know. Sample. The constructor bit masks. I construct the bit mask in the right direction. Like which one are they in this? I don't actually know. I guess we'll just guess. I don't know which like is this cow one or is this cow one. I don't think it's specified, but that doesn't even matter. Because I did not put it in. dp of d1 times dp of d2. Get some runtime errors. Let's see that we got like a buffalo overflow, 15. Shouldn't be that big. I guess if BM B that works. That might just be it. I'm just gonna submit it and see how it goes. I feel like this task was a little bit easier than I was expecting, especially with that minimum magnitude one. If this works, let's see. Maybe we still have a bug. Okay, we definitely have a bug. Oh shoot, because it's not. It's like bipartite matching, but you have to know which ones. Oh, this would take 2 to the 36 time. We want to find the number of perfect matchings. Why am I? That's not what I wanted to do. You would need 2 bit masks, and then that would TLE presumably. I wonder how many. Since I wrote this code and I didn't think carefully, I'm just going to writing it. Just see whether it works, because of course it should give us a couple more test cases. That was definitely a bad move to code this. We should spend a little more time double checking this. Maybe we can get a few test cases though and not waste this code. I just have to work on my sample. So I don't expect this to pass, but maybe we'll take whatever test cases it gives us. Okay, so maybe we're gonna have to think about this a bit more. We still have a lot of time to think about it though. It's not too big a deal. Should TLE pretty easily. Yeah, there we go. There's up to 18 test cases, so we're failing all the large ones. Or sorry, there's up to 8. So we're failing most of the large ones. I guess 2 of them, these last 3, 11, 12, and 13 aren't even maximum. So our runtime is like 2 to the 2n. It's just not great. Okay, well, at least that's quite a few test cases for the brute force solution that we did. Yeah, I don't think you can compute number of matchings efficiently. I think there is like a I think there is if you write, I think I've heard a theorem like this, but if you look at bipartite graph as an incidence matrix or just adjacency matrix, the number of matchings is the permanent of, like, let's just say permanent A, because you just want to pick the permanent A is like the sum of all the number of ways to pick. Like if you remember how you compute the determinant, you look at like ones that don't share rows and columns, right? And you take the product of those and you alternate signs based on like which ones you picked. Here you just take you don't alternate signs. And so you end up with like a matching is one where you don't pick the same row or the same column. So the number of first matchings is the permanent of a square matrix. But I don't believe that's done efficiently. I don't know how you do it. We don't have as many states as I thought. It's definitely a little bit better than like 2 to the 2n, but I don't know. pair of one of them. I wonder if there's a way to use the fact that once you know it for like one of these B1s, B2s will not contain as many bits as the other one. I think we're gonna need to come up with something else. I don't think we can just make this path. This is like n times 2 to the n, which is pretty bad. I'm not entirely sure what we can do here. I don't know. I don't know where to start. We're not on it. Yes, I'm just thinking. I mean, the solution is probably going to be 2 to the n. Like 18 being chosen is quite specific. I don't know. Actually, to get more test cases than I expecting to get without timeline, but still. I guess another thing you could do. Small optimization. We're not gonna get much more, but maybe you got another one. Because I really don't have an idea where to start here. I mean, I convinced myself I had something. I coded it, which is not great, but at least it didn't take a long time to code. It's basically the same runtime. I guess we don't even use like here we really only need to know like our current K, for example. The thing is that doesn't work when you want to do these queries, which is the tricky part. So I think we know how to, I think I can modify this to do it in n times 2 to the n if, or like n squared times 2 to the n. If we're looking at a single query. Which I can kind of, is there a way to combine? Is there to take, well, I don't know, like, because we can do it for a single query. We can just keep track of like K and the bit mask as a state. Thing is you have to skip over some of the K. So you could compute this table. You could compute this. So like here you could easily answer that, but here you don't want to pair G with one of H. Is there a way to like do some sort of like PIE kind of computation where we want to like subtract off and add and like what if you had like a G and an H and then a bunch of G's? Here we can compute this, right? We have some dp of K if there's K G's and whatever the mask is. There could be ones where H is paired off, and you want to know how many don't pair H off. So you could do like dp of K, kind of K plus 2, kind of B M minus like the number. But if you looked at like pairing off H with someone of its, yeah, it gets paired with one of these G's, then that G has to get paired with something else and could follow all cycles or something. It'd still be too many to enumerate, but So I think I was hiding the screen for, sorry if I wasn't showing the notepad, but even if we could like pair off H and we want to like count the number of ways to pair off H, that then you also know which one will pair with the H, which one H will pair with, and then those may or not form a cycle, and then you end up touching a bunch of the other G's, and then you gotta put sparse queries that are kind of hard to answer. Yeah, I don't know. Even then, the fact that we're passing that many is kind of surprising. Maybe we could optimize it, but I also don't have any queries that are like what. Yeah, probably not. And even if we considered, using a single bit mask as our state, you would then have to loop over the cycle you would create, which would require you to loop over like sets of. Yeah, you would then want to know the number of cycles per like a given bit mask. How many permutations are a cycle? And then recurse by removing that cycle. You have to try all cycles. So it'd be like still 2 to the 2n. I'm not entirely sure. Okay. I still have plenty of time. I'm gonna take like a quick 5-minute break. I'll be right back. We'll try to see if we can come up with ideas. There's a good chance we might have to come up with anything and we'll be left with just 10 test cases, which isn't too bad, but yeah, I'll be back. Okay, so we'll keep going. I don't know, maybe we can modify the DP to not do our state the same way. I don't know. Like you want to be able to compute. So if you're looking at like a bit mask from, like I feel like maybe there's some sort of like PIE solution, so inclusion, exclusion. Like if you want to compute DP of some bit mask, it's going to be sum over like the sub bit mask. -1 to the k number of ones and the sub bit mask. Like the sum or the like number of rearrangements in wait, in SB. You take the number of arrangements of everything, you subtract the number of arrangements for every subset of k minus 1, which will do. Does that work? And how would you process that efficiently? Because clearly that's still n to the 2 to the 2n. Yes, because you take the rearrangements jacked up. That seems plausible. You know, I um it might just work. Do you have to, how would you do this efficiently? don't know. Yeah. This summation still takes to the n times. This would work efficiently. Again, to compute the value for a single bit mask. But at least we kind of remove the dependence on k in some sense. And we don't really like find the cycles. So I'm not even 100% this works. Because you want to remove how does this work? You ignore some set. And maybe I'm just gonna try coding that just to confirm that this formula is correct. Not because I think this is gonna pass anymore. Only because I want to see if it's correct. Hard time to convince myself, and we can use the judge to help. I don't like loop over all. It's not even that easy to loop over all the subsets of a given. It's not that easy, but let's just. It's like super naive. And we'll see if EMs or I switch all those bits. Supposedly we'll switch them off is equal to BM minus I. Then this is the valid one, and then make sure we keep the same. Only one with the negative one. I know which one's the correct one. I guess we have to remove at least one, otherwise we're not. That doesn't seem right. Change. That is way worse. I mean that maybe this one just isn't correct. It's possible. I just. I don't know. I don't know. It's maybe it'd be useful to print out. I forgot. Does two string take? Or the way from binary, so that doesn't really matter. Did not print the new one. Okay, so we're gonna see if these match what we're expecting. Of course, there's only one way to assign any ones that's a single one. Here there are three. Oh, but it depends on if they're actually assignable. Shoot. This is, sorry. Make sure. What do I have to make sure? It's not just. It's like the number of rearrangements, and this one has to be rearrangeable itself. Maybe it's the number of I. That's not correct. I guess the base case is if bn and tilde bn equals bn. Well, that doesn't seem right either. In the base case. It's here, and we can see how this gets handled. Oh, sorry, it's not. Should remove that line. Pair them up together, and that's also allowed. So you don't want that case. Well, you either pair. Wait, that is two, right? Hmm. We get this sign, right? But I also need to be taking out the J, so that's kind of silly. Where do I take that account into? I would need to know the number. Yeah, I'm not sure what I'm trying to do here. I confused myself a little bit. Yeah. So we don't want to know dp of I here. We want to know like the number cycles that go through these vertices using the adjacency list. I don't know if you can compute that efficiently, let alone this efficiently. But you need a different function to compute that, and then you would do dp of bm minus I. Otherwise, this won't probably work. I guess in that case, you could do that. If you could do that, maybe we'll get something. But like, we're not gonna pass more test cases, not previous passing, but maybe it's a different DP technique, and maybe we can get rid of the state in some way. Like maybe you process these in a certain order. Don't see what we can do here. Um, is there an easy way to compute that? If we're looking at I think this is actually pretty similar to a formula for the permanent that I've seen, but. I think there's like a formula based on PIE where you like, you can pick any one in any row and then you subtract all the ones that are invalid for each like possible subset and you get another to the end. Maybe there's an idea there. Because you would remove, yeah, I think we can, let's just say like dp of bit mask equals. So we pick every sub bit mask. We're gonna put the -1 to some power. Times the product of like the count B in row I. How many ones, or how many entries are there in JSMX in row I, which are in B? Can you write this recursively? Because if you knew, if we only consider moving one element, one index in BM. I think this is basically gonna end up being like expansion by minors, like formula. Or no, I don't. Okay, like B equals the sum of B and BM, where BM is size 1. So you move 1 bit. And you have the -1 on all of them. So it's either plus or minus. And this times the sum of the counts of BI. So in this case, does this work or something? I don't know. Plus this doesn't depend on something like that. Oh, no, it's just plus or minus there. They get the signs right. I think the plus minus just applies to all of them. This depends on the sign of, I think, the size of BM. I don't know. I think these, I'm not really sure I'm on the solution here, but I think messing around with this, I don't think this is getting anywhere, like at all. Let's just go delete what we had. Maybe the idea is we remove one bit that's on and BM. Sign, take a plus or minus. And then here, let's just do something naive. I just want to see these formulas. Like, I'm not really sure if any of these are going to work. On and B. Look for each row, and then, okay, so I guess this should be K. Yeah. K not equal to I. It's set. So you get back to this representation. It'd be like, I'm just curious. Roll this output. Negatives. Let's say equals 0 instead. I want to see it. None of them should be negative, but they're all negative, which makes me think maybe I got the. Okay. Because now we're double counting. So I don't want to just include all of those. So I think there is a formula that would work that we choose the end for every query, which we can get out of this, but I don't know how to make this be what we want it to be, because I don't even think this is correct, because this, if this is a correct formula, this over counts. So you'd have to do PIE again. I guess that probably should not be the base case. This should be something like this plus minus. Like, by the way. Yeah, I think you have to do PIE again, and then you end up with something that's still exponential for each grade. Maybe something like, because I think you can still do like expansion by minors too. All right, so let's ignore that for now. I don't think that's going anywhere. I thought maybe you could do some PIE, but these formulas might be correct. So don't take them with too much seriousness, because I don't exactly know how to solve this beyond what the original solution I got was. Okay, so if we did like expansion by minors, we'd have like dp of some bit mask equal to the sum. So look at like some I in BM for some AI J. Okay, sum of AI J times dp BM minus 2 to the I. Or I'll read it a different way. We should treat them like sets. You know, if you did extension on minors, is that? So we'll construct your answer as usual. Okay, so we need to find an I. Now we just loop over all. Oh, this is just the exact, because you have to look at like what the. It's not just. Yeah, so you need 2-bit masks to represent the remaining matrix. That's just the solution. Fact that I was thinking of. That's just I'm not sure. Not sure what we can do here. Don't know what I want to try. Like the issue is, I don't know how we're going to process multiple queries because we can do it for a single query in ways that I believe are optimal for computing number perfect matching by a graph. Like I don't think you can do better than exponential, but the issue is like we can't reuse the work we do, and so that's why I'm kind of focused on trying to get some sort of dynamic programming solution where we can like reuse the values for like an arbitrary bit mass. Because obviously we can do dynamic programming to compute permanent for a given matrix, or like the number of bipartite matchings for a given graph. I don't know what to do after that. I'm just thinking. I'll try to say more, but I don't really have a ton of ideas. Hmm. I don't really have a lot of ideas. I think if we don't come up with something shortly, I think we'll probably end this video because I don't think it's particularly useful. I think if this was in a contest, like I would be pretty happy with this. If this is the contest you're in, like definitely take the 2 to the end solution, 10 test cases. It's pretty good. But we do need to do, I don't know. The thing is, like, this can construct any graph. So there's not like special properties of this graph that can be done. Like, because any graph constructed, you have to be able to still compute the number of matchings on an arbitrary bipartite graph, which the lower bound on that is like n times 2 to the n. So for a single query, you cannot do better than n times 2 to the n. But that doesn't imply anything about doing it on Q queries. But that means somehow you'd have to reuse work, which is why like I can't stop thinking about a dynamic programming solution. I would like to try thinking about like any alternatives, but I feel like you have to do something about dynamic programming over like a single bit mask. So we're looking at, I feel like it has to be some sort of DP on like a single bit mask, but this is the originals we had, right? The thing I originally did is like you could loop over like a cycle to remove and then pick that cycle and then ask how many cycles exist that go through 2 to the or like the set of points you remove off. But that would be 2 to the n times 2 to the n, but what does that actually end up being? Like if you, what's like an approximation of runtime? Did you get like 2? Like if you look at, well, I don't want to bound this. what does this sum end up being, actually? I guess we can use a calculator to ask that. So, let's see what it answers. It's actually not nearly as large as I thought. So if you have an efficient way to loop over, maybe that can work. So we could loop over for a given like bit mask, all the bit masks which are children of it. We should have to find a way to compute that quickly, which I don't know how you can. I don't know how you do that. Like, sure, you could. You couldn't, you don't find a way of officially do that. I guess you could do that. Yeah. You could efficiently loop over like, maybe that would be the kind of way you would do it. Presumably not all these queries would hit, but even then, it's only in the hundreds of millions of possible cases. We have to make sure this is like perfectly efficient, though. We have no spare. So like we would need a function that computes. I don't know how to compute that, but if we had that, maybe this would work. Then we need to compute okay, so if you look over all like sub bit masks and ask, I guess you have to remove at least one, and we have cycles. And you have a factor n here. But let's say we if You just need to find a way to compute the number. So if you could pre-compute this for all like subsets of the graph, maybe there's a chance. A second DP function, and then, this seems like n times like 3. Seems unlikely this would pass, but it's probably gonna pass more. And at this point, like it might be worth trying to get the max number of points possible by just getting tighter bounds on it. So, compute the number of cycles that go through. How many do we have to consider? You would want to know in this case, I'm just gonna implement like another DP here and just see if we can pass even just a few more test cases. I feel like that's a reasonable goal. I mean, I don't think we're really gonna get this problem at this point. Like n cubed times 2 to the n. Not great, but I'm great at my mouth here. Initialize it again. See. Adjacency of curve I and ants plus equals. Have to start the cycle. Eventually get the KM rack. I'll be all right. that's not what I expected. The number of, I guess we're double counting here because we have to include a cycle that includes the first index, otherwise we're gonna double count. So we just want to force ourselves to include. I'm not even trying to implement it correct, but let's just submit. Let's see what we got. No, it's correct at least. Oh, yeah, our array is too big. I just want to see if it's correct. I guess another thing I can do is just make max n like smaller. See if we test it on. All I want to know is if it's correct. We can think about it in a second. There's no point wasting our time if it's not even going to be correct. So I'm just going to make all these arrays. Now we should no longer get memory limits on the sample. It will eventually fail because it will eventually not have the array big enough. Okay, so our implementation is correct. We just need to consider, can we write it in a better way? And then I'm curious, what was the time limit? I'm actually just curious, how does it compare in time limit? If we 17 words. See how many it will pass. If we pass like one or two more, then that's not bad. Reduce it once more. I just want to see if it gets the next test case. That is actually a test case we didn't used to get, right? Interesting. I believe we were at 10 before. Okay, and there's plenty of other efficiency issues we need to deal with. So we end up with one more test case. Maybe there's a way to speed up this cycle. I don't know. You can obviously do things like check if they're in the same strong as their opponent. Check if they're in the same strong as opponent. We could see whether, but like these are only like heuristics because like what if the integer said? So it's not gonna work. But the chance on a lot of large tech is it's not a single strong opponent. Otherwise, there's probably a lot of cycles. And then these are where we can compute cycles faster. Maybe we can do this iteratively. What if we did try this iteratively? The goal here is maybe if we do this iteratively, we can get something that runs a bit faster. We're gonna fix. So fix endpoint. We didn't want the endpoint to be included. Well, depends how I want to do this. Oh, I would move there then. Zero initialize, we're fine there. We're not. We fix this endpoint. Well, it has to be end. Okay. So we're at one at the end plus equals dp. Adjacency into class. Like that. And then instead of using what we had before, we're going to use cycles. Okay, name it DP. That was a bad name. Let me go fix that. Okay, so let's add some debugging output and see. Oh, it's 0. Oh, that's not good. So we do process them in a way that we process ones. So why would that? I guess there's no edge case. If 0, PP1, B. PP1, B at last equals. Okay, so we still end up with something that is not. Let's just say we looked at, to make this easier, let's look at just the ones that end in. Okay, so this turned out to be 1 because I guess 0 is an edge to 0, which is true. Those should all be 1. I guess if we start at 0, you can't get out. Some of those don't look incorrect. So where would be going wrong? No end will be checked, but oh, yeah. I guess no, that's not a problem. I guess we need to do this at the end. That should work, I think. I guess now we need to re-enable the for loop because otherwise this will never work. That was the bug. Interesting output. So somehow our cycles combination is going wrong because we know that our previous code worked, the DP. So which is why I just will submit it. Comment these out. There are, in fact, wait, there should not be 2 cycles. There should be 1 cycle. I guess that's not good. We are double counting, but how would we resolve that? I guess it depends on bits set in B. B. We'll see if that works. Probably not. Oh, there's still a print. Because we got the same test case 11. Okay, that's something. Is there a way for us to eliminate a factor of n here? There's a few things we can do. Let's see if we can get like 1 more test case. We'll store an adjacency list representation as well. Small factor. I don't really know if it's gonna make much difference. I feel like we don't need this many factors of n here. Or at least we shouldn't need to roll a divide to avoid the double counting. Like this should not be necessary, which means we need to. I will just loop up to. Okay, how am I doing this? Let's assume that end is. So we loop over if it's 0. I wanted to avoid looping all the way up to n every time. So we only consider all bit masks that include the first end elements. I can also undo my changes. It should work, but double count. Okay. Get the double counting. We want to know where, I guess that should be. It should be up to less than that. So now we're no longer double counting, and maybe it's more efficient. I don't know. It's a little bit faster. It's like half a second faster on my phone. What about the number of iterations the cycles now does? It's not bad. How does that not work? Oh, because we continued. Else there. Okay. What if we tried implementing the other part iteratively as well? Maybe we'll get another improvement. Okay, what is this? Maybe it's just this is not number one. Because I feel like a lot of these states may not have been queried before. I don't know whether they're recursive or, well, we're not going to do it correctly to begin with. So here, do USB is always smaller, so number B plus equivalent. We get negative. I don't know where we're getting negative values from. Let me go back to the code we had. And see where we know that our original code was correct. Oh, we shouldn't be filling with negative ones in that case. We're incrementing. That could be the entire reason it fails. Comment that, please. That's not, I think I old one. It shrank a little bit more. It used to be 900 milliseconds. But I don't. So somehow, like this is probably where what's gonna run in time. This should run in time. I mean, it's like n cubed times 2. Yeah, that's fine. This is where we're not running in time. And even though we made it iterative, you know, what if the vector is actually better? It has to be better because we don't want to look. But so as we saw, like Wolfram, there's still like 340 million iterations, and then we have an inner loop here. Like there's no way this was gonna terminate. What if there's anything we can pre-compute? Memo does not depend, but cycle memo depends on the actual graph. But if you have like pre-computed some of the transitions, you'd want. What if we do pre-compute the transitions? There's a lot of transitions though, which is the issue. What's can we pre-compute transitions? Is that even possible? So we added. Like if we were to pre-compute these and then submit, you know, how many transitions would we actually expect to see? Let me take the input. I guess probably because let me put that. I can also see how long it actually takes to run because now we know this will run in the exact amount of time as the server will go for the queries, but the queries are constant time. So 193 million transitions. So you can't really pre-compute that because it wouldn't even fit in memory. You know what if we process these in like gray code order where you only flip one bit at a time? Honestly, how do you loop over gray code integers again? I guess we can generate the gray code for. I think this could work. To knock off a factor there. Would this even pass? I don't know. I guess one thing we can do is we could generate the gray code and just like cache it, to be honest. We don't even have to, we can pre-compute that. That might be an efficient way to do it iteratively, but I know we can do it. I think we can do it recursively. So. Okay, yeah. If you're not aware of what gray codes are, they're just like we loop with binary integers where only one bit changes each time. Generate these transitions anymore. That's a place to 18, 0. I'm gonna just test it. Works. Doesn't matter that that's the input. Let's see. I guess I'll test it for. That. What gray codes? What size? Do we generate them all? So we can generate all the gray codes. That would take a little bit of time, but I don't think it's gonna take much. So we can just 0, 0. Yeah. Now, if you want to loop over gray codes of size, or within gray size, all the gray codes of this size. You need to know which bit changes. We should have the ability to look up like inverse powers of 2s. We don't have to loop here. I don't want any extra looping in that part. Inverse power of 2 to the 18 is not that big, right? 260,000. One more pre-computation. Only one more loop. Fast. When I want me to shift. Let's try the small input again. Doesn't work. Okay. We'll XOR it. No. We're doing something wrong here. Let's make sure we didn't mess this up. Just moving over the gray code codes incorrectly. Running this loop, interestingly enough. Oh, it's because I didn't take an N first. That's not really the output I was expecting. We have 36 minutes to. Okay. What indices is more debugging prints to make this a little easier. Okay, so if our indices are like 0, 1, 2, 3. Okay, sure. There's 4 of them. It does make sense that B would mirror those. And oh, but the issue is we're now looping over them and wait. What is the issue here? That seems fine to me. Became so larger. So here they're all just ×2, which makes sense. That makes sense. Oh, but I did want the ones that always include the first one. So I guess. Okay, so there's a couple cases we can do here. If think that condition works. So we just need to figure out what bug we coded into our grade codes. One bug we introduced was we only looped over the ones that we forced it to include one of the indices because we didn't want to remove. So we need to, in this case, which index do we include? We just want indices. Bug. Now B should never be 0, so that should be -3. We actually passed one of the and that's so close though. I wonder how close it is. The thing is, we can still test this stuff individually. This graph, which is it's still got a lot of edges. So one thing that might be useful to do is to at least tell us how long we're taking on each part. Granted. Let's see. At least tell us which part is taking the most time. That's seconds. It's actually a little hard to read. The API. Let's bring in seconds now. That's really close though, 2.4 seconds. Nope. Okay, so the cycles thing takes like 0.3 of a second, even in the worst case, and maybe that can be improved, but I don't think that's what we're doing here. We dropped a whole factor of n by doing the gray codes, which is actually quite nice. For a whole factor of n, we're still TLEs. Okay, so let's try just eliminating the vector creation. Drops all 0.4 seconds. What is the runtime if it's n equals 17? Let's see what that would be here. Okay, so we count this stuff. Is there anywhere I should? Okay. Let's run it on the sample again. What are the run times again? That went down a bit. I think. It's not close to 1200 before. We can always pre-compute the gray codes, but I doubt we're spending a lot of time computing those. I mean, another thing we could do is turn this back into a recursive one and hope that some of the states aren't queried. And we still have our where is the line that initialized that? Or did I delete it? Okay, there's still this. I don't want to run this anymore. And we'll change. I need to take this guy and paste this. Let's try making this change and just see. Or, yeah. Just curious. Set this. But that's not good. How did it pass the sample? How did this pass the sample? I wonder what I did. How would that happen? If PM equals B. I guess it all equals 0. Yeah, that's correct. Well, where did this go wrong, then? I think it should exactly mirror the code we just had that passed. Where did we go wrong? That was my first edition. I want the last edition. Let's look at this. Where did I re-implement this? Okay, so we initialize this with 0, that fails. 4. So somehow we introduced a bug when we copied this code. And this gets wrong answers. I think I'm pretty sure this should give us wrong answer still. At this point, I'm only going for just trying to get any additional test case. By luck, I don't think I have the intended solution, and I don't think I'm going to find it. So it's not really the hope. I don't see where I went wrong because these look identical. And that's not my smallest. How do they transit this imperfect? But still pass the sample. Yeah. How I'm putting wrong answer now. Oh, yeah. Maybe it uses the vector. Of course, now if I run on the big test case, it probably runs faster because most of them won't get queried. Or less of them won't get queried. We also know not all of them will get queried anyway, because I don't think they can all get queried. Because Q is capped. But I guess you could still end up landing all of them. Maybe, I don't know. Let's see what happens. But I'm sure the recursive solution is also slower. So you got one last test case. And just a second. Something else. Okay, so I'm back. Yeah. I mean, this is what I would do in a contest. This is probably the most points that I can get. I don't see the full solution. Although ours is probably within, like, if the time was twice as high, we would probably pass, which, yeah, I don't know if he's on the right track or not. Best I'll be able to do. All right. Well. All right. Well, I think I'm gonna end it here. Hopefully this gives you some insight. Obviously, like the first problem didn't go particularly well, and I should have been a bit more careful with like what I tried to implement without realizing the runtime like right away. But at some point, since I couldn't think of an idea, I really tried very hard to optimize the one we have. I think we got it down to like, well, I guess it's still like 2 to the 2n. So it's not great, but it's the best I could get. We passed everything except for the n equals 18 cases, so it's not bad. It's very close to the time limit. I'm really not sure what the intended solution was. Seems to be a tricky problem. But hopefully you guys felt like benefit from this. I know we spent a long time on the last problem on from one. Because the first two took us about an hour, I think. Number 3 seemed particularly easy. So if you, during a contest, make sure you always read all the problems. You can definitely end up noticing things. That'll be easier. If you spent your time working on the first one, I don't know. Of course, you may have an idea for the first one that I don't. But yeah, okay, I'll end it here. And I'm still thinking about ways I can improve this one, but I really don't know how to actually solve this. But hopefully you guys feel like you gained something. Otherwise, thank you so much.